Good morning, everyone. I'm blessing Chinemerem Dike from Prairie A&M University. I'm here to present our ongoing research, the effects of diversity schemes on enhancing energy detector-based cooperative wideband spectrum sensing in 5G networks. The outline spans from the introduction to future work. The research overview. So the radio spectrum spans from around 3 Hz to 300 gigahertz and is essential for wireless communication. So the spectrum is allocated between the licensed users and unlicensed users. The licensed users are termed the original owner of the spectrum, while the unlicensed users, which our research is all about, is the secondary users or cognitive users. So the birth of 5G gave rise to wireless communication transformation, and it supports capacity for IoT, that's Internet of Things devices, and it supports increased connectivity. So the technology beyond 5G, which had the cognitive radio and dynamic spectrum management, address spectrum congestion. And spectrum sensing enable detection of spectrum holes. And we can see from the diagram here, they're trying to demonstrate dynamic spectrum access, whereby we saw the occupied spectrum and the spectrum holes at the unoccupied area of spectrum. Research problems. So what's the problem of the spectrum is fixed spectrum policy, and it causes spectrum scarcity. Another issue is noise, the noise uncertainty issues, especially in detectors like energy detector, which we are implementing and also trying to optimize is detection efficiency. Another issue is poor detection performance in cooperative sensing because of low signal to noise ratio. The research goals. So our research goal and objective is to develop an enhanced framework for reliable spectrum sensing, to analyze limitations of cooperative wideband spectrum sensing under complex additive wide Gaussian noise channel that is individually and identically distributed. And also to develop an integrated solutions for detection and decision reliability for cooperative wideband spectrum sensing under complex additive wide Gaussian noise that I discussed earlier. And also to optimize the performance of energy detector. So research methodology. So we incorporated two techniques. One, a signal processing technique that is also a diversity scheme too, that is called Maximal Ratio Combining. It weighs each signal proportional to each signal to noise ratio and assigns higher weight to any energy samples with higher signal to noise ratio. So another technique is a K out of M fusion rule that dynamically adjusts the decision at the fusion center to reflect varying channel condition. So the energy detection technique, the characteristic of this technique is simple, and it is also non-coherent technique. So it's computed based on the square magnitude of received samples. And the problem it has is noise uncertainty issues. So in our research, we have this baseline, non-cooperative sensing, because our aim is to demonstrate and implement cooperative sensing technique that is under wideband with subbands. So we have to, in our previous work, we elaborated non-cooperative sensing with cooperative sensing, and we saw the shortfall, as I'm going to discuss in our subsequent slides. But for now, the non-cooperative sensing technique has this character of individual decision-making amongst the cooperative radio and its cooperative radio operates independently, and also they output local sensing decision independently. The good thing about this non-cooperative sensing technique is it has low complexity. It's simpler to implement and is suitable for devices with limited computational resources. The problem it has is its susceptibility to fading and shadowing, and there are also hidden node problems. So that is the problem with this technique. So in our previous research, in a bid to optimize this non-cooperative sensing, we introduced this architecture of some band processing, whereby the received signal is divided into sub-bands, and to make sure that if one cognitive radio couldn't access the primary user occupancy, whether the primary user is in this spectrum or not, and the others can also do that. But the problem we also find out is that low signal to noise ratio also affected its performance. So cooperative sensing technique became a paramount solution for the non-cooperative sensing technique. As you can see from the diagram, there's much about whereby many cooperative radio are in cooperation, and they report their findings to the fusion center, which we evaluate based on their report to know the occupancy of the spectrum, whether the primary user is occupying the spectrum or the spectrum is ideal, and this to make sure there is less interference. When the cooperative sensing technique, the cognitive radios are assessing the spectrum. So as you can see, there are multiple cognitive radios in detection. They share their data with the central node, as I discussed, and this improves detection reliability. Another characteristic is positive. It has that it's robust against individual failures. But the drawback is, again, from our findings, is greatly affected by low signal to noise ratio. The technique that's used for this cooperative sensing is, as from research, is all rule, majority rule, odd rule, and K out of N rule. And we are going to implement K out of N rule in our research. So the literature review, as I discussed earlier, our previous work that we published in this conference, we find out that we identify poor performance of cooperative sensing strategy under low signal to noise ratio. Also, alongside with the author, A. Sharma et al., they also find out the same issue. But the only thing in our previous research, we were not able to provide mitigation strategy for these issues. And this is what we are trying to solve in this research. So the proposed solution from our previous findings, we developed enhanced cooperative wideband spectral sensing framework, whereby we divided the received signal into sub-bands as well. But now, in order to mitigate against the poor signal to noise ratio that we encountered in our previous research, we implemented maximal ratio combining and K out of M fusion rule. The maximal ratio combining assign higher weights, as I said earlier, to higher signal to noise ratio with better signal to noise, to signals with better signal to noise ratio. That's channel quality. And also this enhances detection reliability. And the K out of N rule perform optimization under varying signal to noise ratio and channel condition. And also it also enhances energy efficiency. So in our results, so I presented from our previous work, which we published as well, where we implemented only K out of M fusion rule with 6 cognitive radios in cooperation at K equals to 2. So we use the metric probability of detection and probability of false alarm, and also comparing our findings with a non-cooperative sensing and cooperative sensing under different. We looked at 5 sub-bands, and as we can see, when we implemented only K out of M, only K equals to 2 for the K out of M fusion rule, the performance of the cooperative sensing and non-cooperative sensing is almost the same. So the cooperative sensing didn't show any much effect. So which means signal to noise ratio, or poor signal to noise ratio affected it. As we can see, minus 20 decibel. Under very poor signal to noise ratio, the cooperative sensing behaves as the non-cooperative sensing. So in this, our solution proposed method, we integrated maximal ratio combining, which is the diversity scheme, and also the signal processing technique, with the K out of M fusion rule, the same condition of 6 cognitive radios, and the K equals to 2. So as we can see, when the signal to noise ratio is minus 20 decibel, under the same low false alarm rate of from 0.1 to 1, we see a progressive improvement. The cognitive radio, the cooperative sensing had show better improvement than the non-cooperative sensing. This can be shown clearly when we use another metric, probability of detection versus the signal to noise ratio. Under the same condition, when as we can see, when we didn't implement the maximal ratio combining in our previous research, when the under probability of false alarm of very low, that is 0.01, and signal to noise ratio of minus 20 decibel, we saw that the cooperative sensing and the non-cooperative sensing, they couldn't detect anything. They are just in the same level. So implementing maximal ratio combining with K out of M fusion rule showed a very big improvement. So the cooperative sensing under minus 20 decibel, minus 18 decibel showed, and at the probability of low probability of false alarm of 0.01 showed very improved detection performance. So in conclusion, so the integration of maximal ratio combining with K out of M fusion will improve detection accuracy under low signal to noise ratio in complex Gaussian noise. And it achieves higher detection probability and lower false alarm rates than traditional cooperative and non-cooperative methods. So the maximal ratio combining mitigates noise uncertainty and optimized case selection ensure robust sensing in challenging conditions, and also provided energy efficiency. So because this is an ongoing research, we started with additive wide Gaussian noise. we'll be extending our research to using in other feeding channels like the Prairie feeding channel, Russian and the Nakagami feeding channel under individually and not identically distributed conditions. So we are also trying to improve spectrum sensing reliability in 5G and IoT devices by dynamically adjusting detection threshold in response to temporal channel variation and real-world deployment challenges. And we also will be employing machine learning to dynamically select optimal K in the K out of N rule, enabling autonomous adaptation to changing conditions. So these are the